Hi everyone, welcome to today's session. Glad to see a huge number of turnouts here and a very interesting topic that we're discussing today. Before we jump into the meat of it and I introduce you to the subject matter expert of the day, I would quickly take 2 minutes to talk about who we are and why we do what we do. So essentially, today's session is being hosted by Interview Kickstart. And if you talk about who Interview Kickstart is, we are essentially a tech up-leveling platform, which has a legacy of over 12 plus years. And we are the market leader in the Silicon Valley, which is widely recognized as the heart of everything tech. So till date, we have around 27,000 plus enrollments. We have 200 plus hiring partners where we tend to place our students in. And every one of our products is essentially domain specific because we understand that when it comes to tech, it can't be one size fits all. In addition to that, the thing that we are most proud of is our Mang Plus and AI mentors, who are the best of its kind that we see in the in the landscape today. And to testament of this fact, we have also been recognized by the Time magazine as well as GSP as one of the top 100 edtech companies to operate in the global level at this point in time. Now, to add to what I was talking about, our tech partners or the subject matter experts that we have. If you look at the screen, you see the kind of eminent personalities who are out there who work with us in tandem to bring impeccable knowledge in your hands. Before we proceed, there's one thing I would like to do though, and that is to launch a particular poll so that we are a bit data-driven about who is our audience we are catering to and what are your needs like so that we can improve ourselves as we go forward. The whole idea of why we do what we do is because we want to democratize the AI learning, and what better way than to bring it from the people who are actually leading this at the forefront of all the Mang Plus companies out there. Today, I would like to introduce you to Jivendra Singh, who is an eminent software engineer and has over a decade of experience. Welcome to the session, Jivendra. Really nice to have you out here. Yep. And I would hand over to Jivendra to take it from here. And all the best. Hope this is turning out to be a really great learning experience for everybody in the room.
Yeah. All right. Thanks, Moin. Thanks for the intro. What I'll do is I'll share my slides so that I have the control here. Yeah. Sure. Okay, let me begin sharing my screen.
We can see a screen.
All right. Thank you. Cool. Okay. So hello, everybody. Good evening. So welcome to this masterclass on system design of Claude Code. So today we're going inside Claude Code, which is Anthropic's agentic CLI, and it has crossed $1 billion in revenue since becoming generally available in May 2025, right? Now, before we touch any architecture, let me paint a picture of what actually happens when you use this thing. So imagine you are in your terminal inside your repo. You describe a new feature you want to implement. Plain English, few sentences, and then here's what happens next, right? Claude Code reads your code base. It searches for the relevant files, opens them, understands the existing structure, then it edits the code, adds imports, writes new logic, updates config, etc. Right? And then it runs your code or your tests to check if anything broke or not. So if a test fails, it reads the error, fixes the code, and reruns, right? And all of this happens in a loop. Read, think, act, and then repeat. And that too without you pressing a single button, right? Now to follow today's session, let me introduce the key ideas you will hear throughout. The first is the model's working memory, what we call as the context window. Everything the model can see at once has to fit inside a fixed token budget. Now you can think of it as a RAM that gets wiped every turn. And what is in that window? So there are multiple things in the window. Your conversation history, which is every message you have sent and every response that you have received so far. Then tool definitions, which is a structured description of each capability the model can use, like a read file, which can take a file path, and return the file contents, or maybe bash takes a shell command and returns your standard output or standard error, whatever, right? And also the actual content, right? The files the model has read, the test output it has got back, right? The errors it saw. So all of that competes for the same fixed space. Now with older Claude models like Sonnet 4.5, that window is 200K tokens. The newer Claude series 4.6 and above bumps it up to 1 million tokens, which sounds enormous, but even 1 million might not be enough. And most of the time it is not. Why? Because a single medium-sized code base can be tens of millions of tokens. So one tool call that dumps a big log file, right, can eat 50K tokens in one shot. A long conversation with dozens of tool results will fill the window in minutes. So no matter how large the window gets, you would still need ways to manage it, like summarizing the old conversations to free up space for the newer ones, which is technically called as compaction, or maybe deciding what to throw away when the window is full, which is also called as eviction, right? And maybe also reusing parts of the prompt you have already paid for so that you don't pay again, which is caching, right? Caching of tokens. Now, that's the architecture that we're going to talk about today. So managing this context window budget would be half of the design itself. The second idea is how the model takes action through what we call a tool call. So the model can't actually read files or run commands on its own because it's just a text generator, right? So we give it tools, read file, edit file, bash, etc. for running these shell commands, maybe grep tool for searching text across files. And then model outputs a structured request like call the read file with path this. And then Claude Code, the program running on your machine, picks up that request, actually reads the file, and then feeds the contents back to the model. And then the model thinks and the program acts, right? So these are the two ideas. And there's one more, which is the third idea, which will tie all of it together, which is your agent loop. The read, think, act cycle I described a moment ago, that's the agent loop. In the research literature, this pattern is called REACT, reason and act. But there's an important distinction. You need to remember this. The model does not act. The model does not act. The model is just the text generator. It reasons and it outputs what it wants to do. And the agent, which is your Claude Code, the program on your machine, is the one that actually acts, right? It reads the model's request, executes the tool, and feeds the result back, right? So remember this, the model reasons, the agent acts. That's why it's called an agentic system and not just a chatbot. And then agent keeps the cycle going, reason, act, observe, reason again, until whatever task you're doing, that is done. It's like a while true loop, right? And designing what goes inside that loop, what guards it, what feeds it, and what stops it, that's what this entire session is about, right? So the question we are answering today is how would you design Claude Code, that whole pipeline, if you had to build it from scratch? So every slide going forward of this agenda is going to add one piece. We'll tackle how the context window gets managed when it fills up, how tools get validated and sandboxed before they touch your files, why the system uses these different models, a powerful one for reasoning, a fast one for quick checks, and so on and so forth, right? Now, let me show the agenda for today. This is the agenda. You'll see some 12 sections here on the agenda. Each one covers a different aspect of the system. We'll start with the foundations here first, and then requirements, and move on to the architecture, scales and constraints, the model API, safety permission, memory and context, and whatnot, right? All of this will come together at the end. And going through this agenda, we're going to make 22 design decisions, right? And each part here, each part of this agenda is going to add decisions one by one to a larger architecture diagram that we will end with, right? With all the 22 design decisions that we will take at the end, right? Okay, moving on. So foundations. So let's look at this matrix, the 2x2 matrix here. There are two dimensions here, steps and decision making, right? So first is how many steps does it take? If you look at these columns, the single column and this multi-column, how many steps does it take? Is it a single action or is it a multi-step sequence? That's your columns here, right? And then second is who makes these decisions? If the code follows a fixed set of if-else rules, same input always gives the same output. Basically, it's deterministic. That's one kind of a decision making. And then the other decision making could be the one done by the model itself, right? Where the AI model looks at the situation and decides what to do. So it might choose differently next time, even with the same input. That's something that we call as non-deterministic or stochastic, right? So steps, single or multi, decision making, deterministic or non-deterministic, right? Now, if you look at this one, right? Here, there's a single step, and here your AI model is involved, then you'll have a chatbot. Here, the step is single, and it involves a deterministic code. That's why it's a script. This is a workflow where the code is if-else, and the steps are multi, right? Agent is something which sits here, right? Which is both a multi-step and model-driven, right? So multi-step, that's already clear to you. And when we say model-driven, then we are introducing a level of non-determinism here, which is what we will tackle in this whole session, right? So what are we building? I already told that, but let's reiterate it again. So look at this. Look at this text here, right? And just read it with me. We are building a CLI tool, right? Which will run inside the developer's system, right? Run in their repository, which can read and edit code, run shell commands, search the code base, can take multi-step actions, resume the sessions that they are already having. And it should also be integrated within their editor. And underlying, it should use an LLM as a decision engine. Now, who's going to use this tool? Software engineers are going to use this tool on their laptop to do multi-step coding tasks, right? And how long? It could be single session, minutes to hours, multiple sessions, whatnot, right? So anybody who has been using Claude Code all this while, they know we are all burning our nights using Claude Code, right? And there's a lot of memes and jokes that you'll hear about people using Claude Code. Okay, since we are doing system design here, so we have to start with the functional and non-functional requirements. So these are some of the things that it must do. So the first thing is it should be able to read and edit files, right? Open a source file, change a function, update a config, right? It should be able to run shell commands, like running your tests, installing packages, checking your build output, stuff like that. It should be able to search the code base, right? It should be able to find every place a function is called or a variable is used, right? It should be multi-turn chat, right? You can ask a follow-up question and it should remember the whole conversation that you had so far. You should be able to resume sessions, which means that if you chose to close your terminal, you come back tomorrow, then you can pick up right from where you left off. You should be able to rewind and undo your actions. So if, let's say, the agent made a bad edit 3 steps ago, 4 steps ago, you should be able to roll back to that point. It should run in your IDE. It could run on any communication platform that you're using, Slack, Teams, whatnot. And there should be also a headless version of it, right? So same agent, but different surfaces, right? Then you should be also able to plug in external tools via MCP. You should be able to connect to GitHub, Jira, some database, or even your internal APIs, right? And then it should support user-defined extensions. Like users could add hooks, some custom rules, some project-specific instructions without touching the core code of your agent, right? You must have heard of skills that people are building. So that's what a user-defined extension is. It's an example of user-defined extension. Then the non-functional requirements. Now, how well it must do all these things, right? All these numbers that you see here, these are just illustrative requirements. They may not be exactly what Claude Code uses internally, but they are the kind of targets you would set if you are designing the system yourself, right? Time to first token, here we are taking it to be under 500 milliseconds. There should be there should be the possibility of self-healing, right? It should survive, let's say, tool failures. There should be safety built in. You should not be able to run any rogue commands on your system, right? The cost, well, that's very debatable. It should be less than 50 cents. That's what we're targeting. Then portability, right? It should be able to work on different operating systems like Mac OS, Linux, Windows, whatnot, right? And there should be also a functionality of model routing. It should support different models. If we are talking specifically about Claude Code, it lets you choose models that are from Anthropic. But if we are building a coding assistant like this, then we would probably want to support any model, not just Anthropic's models, right? Okay, so what we are not building, that's also important, right? This is not a chatbot. It's task-oriented, not just conversational. It's not a replacement for IDE. It just complements it, right? It is not a replacement for your CI. Again, it just augments your CI. It's not a shared multi-user environment. It's meant for one developer, one session. And we're not going to train any model here. We're just going to consume a model. That's what we'll do here. So we have finished two parts, right? We haven't yet made any design decisions yet. Let's talk about scale and constraints, and going forward in the next parts, we'll try to start with some of the design decisions. So let's quickly look at some of the scales here, some back of the envelope numbers. Again, these are illustrative. They are not published by Anthropic. This is something that we would estimate before we start to design any particular system, right? And you know, you must have appeared for system design interviews. These are something that you do there. So we're saying that we probably have 50K concurrent users at peak, roughly 2 million sessions per day. Then a median number of 15 for number of turns in a particular session. Then we might have 1 to 10 tool calls every turn at max. We might want to parallelize our tool calls wherever it's safe to parallelize them. Then we'd expect 5K to 30,000 tokens per turn after caching. Then the cost ceiling we are putting here, which is 50 cents per complex request. And the time to first token, we already told that we'd keep it at 500 milliseconds. So these are some of the numbers that we'd be targeting. Okay, now let's quickly talk about some of the specific constraints here, right? So what makes this Claude Code CLI different from your usual command line interface? So these are some of the constraints, and each of these constraints are going to drive some of our design decisions later. The first is the finite context window, right? We covered this already, but it needs repeating because it shapes your half the architecture. The model's memory is the hard cap. Then it's a stateless model. The model doesn't remember anything between the turns. Every single turn, you have to resend the entire conversation history from scratch. And that's why compaction, caching, and all those strategies matter. We'll get to that. Then the per token pricing, right? Every token you send costs money. So longer the conversation goes, the more expensive it is going to get. That's why caching, compression, and all of them, all those techniques, they're not optional. Model versions drift, and this is very important. You ship the product, the model provider updates the model, and suddenly your system starts to behave differently. And Anthropic has published a lot of incidents on their blog where they talk about such scenarios, and we'll cover some of those incidents later. Prompt injection, this is probably one of the hardest security challenges at the moment. So when the model reads a file or fetches a URL, malicious content in that output can trick the model into doing something it shouldn't. That's a whole threat category, which we'll address in the safety section. And non-deterministic output, yeah, this is something that we struggle with a lot. And as developers, we have always been used to build all these deterministic systems and taking the reliability up to 4 nines, but we are in a different world now. Non-deterministic output means same input, but different output every time, right? So how do you write and test for a system that doesn't give the same answer twice, right? So these are some of the constraints which this Claude Code CLI would be dealing with, which is very different from a normal CLI. This is our part 4, which is defining our high-level architecture. Now, when we are trying to think of the architecture for this coding agent, which is Claude Code, we have 2 architectural styles at hand. On the left, you see it's a multi-agent graph. You have multiple specialized agents talking to each other, like crisscrossing edges everywhere. This is the approach which probably Google Anti-Gravity takes. So Google Anti-Gravity is another coding platform like Claude Code. So it is designed to orchestrate multiple sub-agents in parallel across different workspaces, with separate agents handling everything from research to implementation to testing. It sounds powerful, and it is, but when something goes wrong, which agent made the bad call, what went really wrong, it's very, very difficult to debug that. And then also the failure could be in any edge. On the right-hand side, you see there's a single main loop, one primary loop that dispatches to different tools like read a file, edit a file, bash, grep, whatnot. This is the approach Claude Code and Cursor, which is again another coding tool, have converged on. Now, to be clear, Claude Code isn't purely single-threaded. It can spawn sub-agents for subtasks, each with its own context window and its own tool allow list. But the key difference is those agents or those sub-agents are still the same model controlled by the same primary loop. And that's very different from this multi-agent graph where fundamentally different agents, they coordinate together in a peer-to-peer fashion, right? Here in Claude Code, the primary loop stays in the control. So any failures that happen, they stay localized. And you can actually debug it. In fact, when Claude Code spawns a new subagent, those subagents are not allowed to spawn their own subagents. So even if there's a spawning of a new agent with its own context window, it still is limited to one level, right? So here is our design decision 1, right? This is the first design decision out of those 22 design decisions that we wanted to make, as promised earlier. Pick the single main loop. Pick the single main loop, right? Because debuggability is going to beat any sophistication. So when your system is already unpredictable by nature, because you are dealing with stochastic, non-deterministic models, you want to be able to trace exactly what went wrong. And a single loop like this makes things possible. So this is our design decision 1. Pick the single main loop because debuggability always beats sophistication, right? So here is the entire agent in 20 lines of pseudocode, right? Recall the React loop, which we talked about in the opening, right? Reason, act, observe, and repeat. Here's what it actually looks like in code. The user asks a question or gives a task. Claude Code takes that current question, any previous conversation history that it might have, the list of available tools and stuff like that. And it sends all of that to the model here, right? Now, to answer this question or to finish this task, the model might need more information. So it tells the agent that, hey, these are tools that you should invoke. Read this file, run this test. And then the agent executes the tool. The model doesn't execute the tool. The agent executes the tool, gets the result, and then feeds it back to the model. Now, the model would have more context. So it can then decide, do I have enough to answer this question or finish this task, or do I need another tool call? If it needs more, then it asks for another tool. If it has enough, then it responds with the final answer, right? And that's your loop. This is the loop here, right? The model keeps requesting tools until it has gathered everything it needs to complete the task. The entire brain of this billion-dollar product is in this while loop, right? So this loop is deliberately very small and dumb, right? All the smart stuff, right? The validation, checking of permissions, schema validation here, checking of permissions, sandboxing, caching, everything lives in the layers around it, right? Not inside it. And that's your design decision too, which means keep the loop small, push the complexity to the edges, right? So this is what your pseudocode looks like. Of course, it's more complex than that, but it's enough to get an idea. Right. Now, here is our architecture. And this is what we will keep coming back to in the rest of the section. Every design decisions we make from here will land into one of these 5 layers. So these are the 5 layers from top to bottom, from user till the end. So the first layer here is your UI layer, right? UI, TUI, right? TUI stands for terminal user interface. So it's the custom built rendering layer, right? This layer handles all the surfaces, your terminal, your IDs, extensions, some communication platform extension integration like Slack integration, or even it can run headless in your CI pipelines. So its job, the first layer here, its job is to take the raw model output and present it to whatever surface the user is on, whether that's a human at a keyboard or a CI pipeline expecting some kind of a JSON. Then layer 2 is your agent loop, right? This is the while loop from the previous slide, the one that drives the entire conversation. It takes the user's message, sends it to the model, gets back either a tool call, a final answer, and keeps cycling within it. Everything else exists here to serve this loop. Then below here, there is the layer 3, which is the tool dispatch. This is a whole pipeline that we'll cover in detail later. This is responsible to validate, check permissions, and then execute a tool call, or even trim every tool call before the result goes back into the model. It's a gatekeeper between the model wants to do something and the system actually does it, right? Then you have the layer 4 here, which is your permission and sandbox. This layer decides what is allowed and what is blocked, right? So there are multiple lines of defenses here. One could be where a permission check that decides whether a tool call should proceed or not. And then you could have kernel level sandboxing, so that even if the permission logic has a bug, the operating system itself can stop the damage. And we'll cover all these defenses later in the slide when we are specifically focusing on permissions and sandboxing. The last layer is your model API, right? This is where the system actually talks to the Anthropic LLMs via the REST API. This handles cache management, token streaming, model routing, right? Deciding whether to send this particular call to Opus models or Sonnet model or Haiku model based on the task, right? Now notice something about this stack. The model is at the bottom, not the top, right? And that's very deliberate. The model is a dependency, you call it, you get a response, you move on. But everything above it, the loop here, the tools here, right? The permissions, UI, everything. This is what is called as harness. If you have been following the agentic AI space, you would probably have heard the term harness engineering. You must have seen the ads of it as well on Instagram or Facebook, wherever. So, well, this is what it actually looks like for a coding agent like Claude Code. Now, think of it this way. The model here is non-deterministic. Same input, different output every time. The harness is opposite. It is deterministic. Same tool calls always go through the same validation, the same permission check, right? The same sandbox every time. And there are no exceptions to that. So what you're really doing here is wrapping up predictable, reliable layer around a unpredictable brain or a model. And that's what makes Claude Code reliable, even when the model inside it isn't, right? And that's why these layering matters, right? So if Anthropic ships a new model tomorrow, then only the layer 5 changes here. The harness layers, layer 4 to layer 1 here, they will be untouched. And this is our design decision 3 out of those 22 design decisions that we want to make, layered separation. Each layer owns one concern. Each layer will evolve independently. So you can change the UI without touching the tools, change the sandbox without touching the model. That's the whole point of these layers, right? Okay. Let's quickly look at a sequence diagram to understand how all these 5 layers are working together. Let's maybe trace one real user message through the entire stack. So here in the step 1, let's say the user types a message in the terminal on the TUI, and the TUI captures input and then passes it down, right? The message hits the layer 2, the agent loop here, right? The loop is going to package up the user message, the conversation history that has been there so far, and the list of available tools that it has, and sends all of it to the model via the layer 5, right? Now, in the step 3, the model looks at everything and decides, I need to read this auth.py first before I can fix anything. So it responds with this tool call that, hey, go and read author.py. And this is not the final answer. The task is not yet finished. It's just a request for more information, right? And then the tool goes to here, layer 3, right? The tool dispatch, right? And then the dispatch pipeline, the tool dispatch pipeline, this whole thing is going to validate multiple things. It is going to first validate the input, right? If you are asking to read file, have you provided a file path or not? Is the file path valid or not, right? Things like this. So this is going to pass it to the layer 4, which is the permissions layer here, permissions and sandboxing, which checks whether is this tool allowed. Is the path, because if you're asking to read the file, is the path inside that project directory, the one where your terminal is running, the Claude Code terminal is running. And because in this case, the one that you see on the diagram, it can actually read it. It's already approved automatically. So no human prompt is needed. But imagine the model has instead asked to run some kind of a bash command saying, delete the node modules folder and reinstall all packages. Now, that's not a read tool call, right? That's a destructive shell command. So the layer 4 here, the permissions layer, right? It would escalate to the human saying, well, Claude Code wants to run this command. Do I allow it or do I not allow it? You would see that yes, no prompt in your terminal, right? And nothing happens until you approve it. So that's the permission layers, the permission cascade in action, right? Reads will sail through, but anything that could damage or delete something gets a human checkpoint. Although in this case, read was allowed, so it was allowed, the file contents were served back to the loop. However, it doesn't end here. The loop continues until the model returns a text response. So probably the step after reading the file contents would be The loop sends everything back to the model again. Now the model has enough context to see the bug that was originally asked for. Maybe it's a missing null check. So it responds with another tool call, maybe edit auth.py, and then add that fix, right? The edit again goes through the same dispatch and check permissions here, that the one that you see here, right? Same permission, same check, same sandbox. And then finally, the model gets the edit confirmation back, decides it's done, and then probably responds with a message saying that, hey, I've fixed the null check in auth.py, line number 42. That's a text response, not a tool call. That's why the loop will exit. And the answer flows back to the layer 1, which is the TUI layer here, which renders it for the user. So that's one message flowing through all the 5 layers. Every message you send goes through this exact same path. Now, part 5, CLI surface. So the question here is, where should the agent live? So we have multiple options here, 3 options primarily. One is it could be a web app. Web app will have a rich UI, but the developer has to leave their terminal. And a web app cannot directly touch files on the disk or run shell commands. You would need some kind of a backend relay for everything, right? You could have an IDE plugin. You are inside the editor right next to your code, but you have to build a separate plugin for each editor, for VS Code separately, for JetBrains separately, and so on. And the shell access, again, is also limited. Most plugin APIs don't give you a full terminal. However, the VS Code extension of Claude Code is pretty good. I work with it most of the times. It works really well. The CLI, it is something that runs right in the developer's terminal inside their repo. Native file system access, you get the full shell, and it's scriptable, right? So the same tool call that works on developer's laptop will also work headlessly in GitHub Actions pipeline. But there are some downsides to it as well. You will have limited rendering and no built-in login screen and stuff like that. But CLI is our choice here because developer is already in a terminal running their Git commands, NPM commands, Docker, whatnot. So a CLI agent meets them where they already are, right? So there is no context switch that is needed. And that's our design decision 4 out of those 22 design decisions, where CLI is your primary surface because the developer is already in the terminal, right? So Claude Code, they have chose a custom CLI, right? Now, since we have picked CLI, so we need to render the output, right? And why build the terminal UI from scratch instead of using, let's say, an existing library like ncurses? Ncurses is a standard C library that most terminal apps use for if they have to draw something on your text-based interfaces, right? Now, because this is not a static terminal app, it's a streaming one. Tokens are going to arrive from the model one at a time while the user is watching. So in between the stream, a tool call might fire, and its output needs to appear in line in the terminal itself. You would have probably progress bars that are going to update live, and the user needs to scroll back through previous outputs while, let's say, the new text is arriving, right? And ncurses was not really designed for any of that. So Claude Code has built their own rendering pipeline. The model, right? Haiku, Sonnet, whatnot, that model, it's going to stream the tokens via SSE, which is your server sent events. And then these tokens feed into a React component tree. Yes, React, the same framework that is used for web UIs, but running in the terminal, not on the browser. Then a layout engine called Yoga, which computes the flexbox positioning. So if you understand CSS, you know what flexbox is. So this layout engine computes flexbox positioning. And then Ink, it's a terminal rendering library, which does like a diff and reconcile, which only updates the parts of the screen that actually have changed, and then writes that final output to the terminal's display. So this is the custom TUI architecture, which Claude Code has. And this is our design decision 5, to have a custom TUI where, because streaming output is a system, right? It's a design concern, right? It's not just cosmetic, it's a design concern really. And what Claude Code claims in their blogs, that this is just 2,700 lines of code re-implemented in TypeScript from scratch. That is the price they have paid for building their own custom TUI. All right. Now quickly look at the input state machine, right? Because terminal isn't just just rendering your output; it also has to handle user input. And input in Claude Code is not simple because the terminal can be in these 4 different states at any time, right? It could be idle, right, where it is waiting for the input, nothing is happening. The cursor is blinking, waiting for the user to type something. And then the subsequent state could be where the user is composing a message, the user is typing. Now, this should support multi-line input. It should support pasting stuff, right? Paste detection. And also your command history, just like your regular shell, right? Where you can press the window up button and you can go back to the commands that you have typed. Then it could be in a running state where the user has hit enter and the agent is working. Tokens are streaming in, tools are executing, and the user is seeing the live progress, right? If something goes wrong or something takes too long, then you can interrupt it using Control-C, right? And then rewind, right? So rewind is a very important component here. Let's say the user pressed the escape twice quickly. This should roll back the conversation to the last checkpoint, right? Which means it should also undo the most recent tool call and the model responses, so that the user probably wants to try a different approach maybe, right? So the transitions here that you see here, where it can go from idle to typing, typing to running, running to idle, running to rewind, rewind to idle, right? These are straightforward, right? And the key insight here is that interrupt and rewind here are not afterthoughts. They are built into the state machine here as first class transitions. Because in an agentic system, the user needs to be able to stop or undo the agent at any given point of time. And this is our design decision 6. Treat input as a state machine, right? And interrupt and rewind should be our first class citizens here, right? Okay, distribution. And that's very important for any software product to actually be successful if you're able to distribute it to everybody. So how does a developer actually install this thing? So yeah, they could do pip, right? Familiar to all the developers. But again, here the updates are going to be slow because you're going through some kind of a package review process. You could do standalone binaries, right, where no dependencies are needed. But then the download is going to be large, and again, if there are updates, it means you have to re-download the whole thing. You could do npm. Everybody knows it. It has a very big developer reach, and also easy updates with a single command. But again, it requires Node.js to be running on the machine. What Claude Code does is this npm plus a native binary. So npm handles the distribution, right? Developers already have it. Updates are just one command, and it works on every operating system. But the actual execution does not run through the Node.js. Instead of that, the npm package includes a native binary, which is a pre-compiled executable built with something called bun, which is a JavaScript runtime. So npm is your delivery truck, and the binary is what actually runs on your machine. That's why it starts fast, right? And it does not need you to install anything else. So the install command is pretty simple, right? You just do npm install and maybe install it globally, then -g Anthropic Claude Code. One line and you're ready to go. And the final artifact is some 10.5 megabytes for the JavaScript CLI, which is delivered via npm. And plus, there is also a 188 MB binary built using bun, which is the JavaScript runtime. So you have a fast JavaScript runtime, zero install time dependencies, nothing else to download or configure. And this is our design decision 7. Distribute via npm plus native binary so that you have maximum reach and minimum friction, right? Now this brings us to part 6, which is about tools, which are the hands of your agents, right? Right. What is this tool contract, tool design? So every tool in Claude Code, whether it's reading a file, editing a file, running grep commands, bash commands, all these 50 plus tools, all of them, they have to follow the same contract. Think of it as a checklist. If a tool does not fill all these five parts that you see here on the screen, then it does not get registered. So the first one here is a schema. So this defines what inputs the tool accepts. For example, the read file tool accepts a file path as a string. If the model sends something that does not match the schema, like let's say a number instead of a file path, the call is going to get rejected before it even executes, right? So the schema is something that guards the model's output. Then you have permissions here, right? So permissions are something which this declares basically what kind of access the tool needs, right? A read tool is low risk. A bash tool that can run any shell command is a high risk. So the permission part here tells how to handle it, whether the tool should be auto-approved or should you ask the human, or maybe even block it entirely. So it guards the user's system here, right? Concurrency safe, yeah. So this is like a true or false flag that is available on every tool, which says whether it's safe to run this tool in parallel with other tools. For example, if you are reading 5 files at once, fine. Editing 2 files at once, that could be dangerous. You could get some kind of race conditions. So this flag in every tool tells you whether it's safe to do parallel calls or not. Then read only, right? So read only is another flag on every tool. So if a tool only reads and never writes, then it can skip the permissions prompt entirely, right? No need to ask the user, can I read this file, right? So this keeps the experience fast. Then you have this render function in every tool, which tells the UI how to display the tool's results, right? Because a file read might show a code block with syntax highlighting, right? That you need to display different kinds of text in different ways. A bash command might show a terminal output. So the UI is part of the tool, right? It's not an afterthought, okay? Now, each part here prevents some kind of a failure. If you skip the schema in your tools and there's a bad input, it is going to crash the tool. If you're going to skip the permissions, your agent is going to run wild, right? You skip the concurrency flag here and parallel calls may corrupt your files, right? So the contract here is the design, right? And that's our design decision 8. Every tool must fill all these 5 parts. If you skip one, you are losing some kind of a guarantee on that tool. Okay, now let's quickly talk about the tool dispatch, right? Every tool is going to go through this complete pipeline. You recall, I was talking about the tool dispatch pipeline that we'll cover later. This is it. So we define the contract that every tool must have. Now let's look at what happens when the model actually calls a tool. So every single tool call, whether it's a read file, edit file, whatnot, they go through the same pipeline here before the result makes it to the terminal, makes it to the model, right? So schema parsing, right? So the input of the tool gets validated by something called Zord, which is a TypeScript schema validation library. So if the model said read file, but sent a number instead of a file path, this stage is going to catch it immediately. Bad input is going to never reach the tool. Then the second is your semantic check. It is the path the model asked for inside the current working directory. So by default, the model cannot read or write files outside your project folder. But if you explicitly allow it, for example, by granting access to, let's say, another directory, then it can. But the point here is that the boundary is enforced here, right? And nothing gets through without your permission, right? Then the third stage here is of permissions, right? So we will cover this layer actually in depth later. But the main idea here is that this layer decides, should this call be auto-approved, or should it be escalated to human, or maybe blocked entirely, right? So again, a file read will sail through, but a bash command which is trying to delete something will get escalated. Then you have something called a pre-hook. So if the user has, let's say, some set up some kind of a pre-tool use hook, let's say a custom script which checks whether the edited files match a certain naming convention, then it runs here, right, in this step 4 before the tool executes. So this is where generally the teams plug in their own rules, like blocking edits to, let's say, protected directories, or maybe enforcing some kind of a style guide without modifying the Claude Code source code, right? These are like additions on top of it. The layer 5 here is the execution. The tool actually runs, right? Read file, reads the file, bash runs a shell command. This is the only stage that touches the real file system, right? The execute one. And then once the tool call has executed, then you might want to trim the output. So let's say if the result of read file is 50,000 characters, let's say a model ran some kind of a bash command which dumped a huge log file. The full output then goes to disk, and only a 2 kilobytes preview is going to stay in the conversation. So this prevents one large tool result from eating the entire context window. And then you have something called as a post hook. This is the user's post tool use hook here. This is where you would probably plug in some kind of a formatter, let's say a linter or a audit logger or whatnot, right? For example, you could say that I want to run prettier on every file the agent edits, or log every bash command to some kind of a compliance file or whatnot, right? And then finally, you append the result, right? The tool's output gets added back to the conversation as a tool result message. Now the model can see what happened, and it can decide its next move, right? Now, why does every tool go through these stages, right? Because the things that matter for every tool, validations, permissions, output trimming, they are built into the pipeline itself. They're not scattered across different individual tool implementation. And this is the whole point, right? If you need to add something new tomorrow, let's say rate limiting or logging, you would add one stage to this pipeline, and every tool is going to get it automatically. You don't go tool by tool, updating each one of them and hoping that you did not miss any tool, right? And that's our design decision 9. One pipeline, all tools, right? So all the cross-cutting concerns will live in the dispatch, not in individual tools, right? Okay, let's quickly talk about the parallel tool calls, because this is something that really makes or breaks the UX experience. So sometimes the model wants to do multiple things at once, right? Say it needs to read 5 files to understand, let's say, a feature. So does it have to read them one at a time, waiting for each of the previous ones to finish before starting the next one? That would be painfully slow, right? So this is where the concurrency safe flag on every tool from the tool contract that comes into picture. So we have two modes here, sequential and parallel. So sequential is where there's one tool call at a time, right? Each is going to wait for the previous one to finish. It is safe, but obviously it is slow. So this is the default for any tool that writes, like edit file. Because if the model edits two files at the same time, and let's say both the edits depend on each other, then you would end up with conflicting changes, right? You know what a race condition is. Then the other one would be this parallel, right? So here multiple tool calls can fire at the same time. And this is allowed when the tool's concurrency safe flag is set to true. So who sets these flags? These flags are set by the tool developer, right? So for built-in tools like read file or bash, Anthropic's engineers have set them. But if you're using MCP tools, so whoever has built that MCP server, they are going to set them. It's a design time decision, not something the model or the end user decides at runtime. Read file is parallel safe by nature, right? You can read multiple files at once and would not cause any conflict at all because nothing is being changed. If you're doing grep searching, that is also parallel safe, but edits, they should be sequential, one at a time. Now, the trade-off here is real in both directions. If you mark too many tools as concurrency safe, you will risk race conditions, two edits stepping on each other. But if you mark too few, everything runs one at a time, and your agent is going to feel painfully slow, right? Now, getting this right is a per tool judgment call, and that is the reason this particular flag exists in the tool contract rather than it being some kind of a global setting, right? Okay, let's quickly talk about the self-healing patterns. So we know things are going to go wrong no matter how great a system you build. Tools will fail. The model API will reject your requests. Permissions will get denied. Now, the question is whether failures, the question isn't really whether the failures are happening. It is whether the system can recover on its own or it crashes and waits for some kind for a human input. Now, Claude Code here has several healing patterns, right? And each of these healing patterns, they exist because something broke in their production and they learned from it and refined their Claude Code. So we will talk about some of these failure modes and which incident drove it. So let's start with this tool result persistence. Now, this is where, let's say, a tool returns more than 50,000 characters of output. Let's say the model ran some kind of a bash command, which dumped an enormous log file. In this case, the full output gets saved to the disk, and only a preview of it, a 2 kilobyte preview of it, stays in the conversation. Yeah, because we have to ration our context memory. We can't dump all those 50,000 characters in the context memory. So we're going to save it to disk, and only a preview of it will go to the conversation. Because before this self-healing pattern of tool result persistence existed, huge tool outputs would fill the entire context window and suddenly start causing out-of-memory crashes. So this pattern of persisting the tool results, large tool results, was born from one incident that happened on Anthropic's Claude Code. Then PTL recovery, prompt to long recovery. So sometimes the conversation gets so long that the model API is going to reject it with some error, maybe a 413 error, which means that your request is too large. Now, when that happens, the system automatically drops the oldest turns from your conversation and retries. So before this mechanism was added, a 413 error would just crash the session. Circuit breaker. So if the same operation is going to fail, let's say 3 times in a row, you should stop retrying. And you'll be surprised. This one actually came from a real incident where the compaction system, the part that summarizes the old conversation to free up the space in context window, it kept failing and retrying in an infinite loop, which burned through API calls and obviously money. So Claude, Anthropic set a threshold that max 3 retries and you should stop. Denial as a result. So when the user, let's say, denies a permission request, say the model asked to run a bash command and the user said no, that denial gets returned to the model as a regular text result, not as a error or exception. Now, why does that matter? Because when the model sees permission denied, the user blocked this bash command, it can then reason about what happened and maybe try a different, safer approach, right? If it got an exception instead, then it would just fail. So this is something, this pattern was introduced because they saw something happening in their production, errors happening in their production because of denial as a result. Idempotent retries, I think they are pretty important in any system that you're building. So if, let's say, your Claude Code is running in a headless mode, where it's, let's say, running in some kind of a CI pipeline with no human present, then failed operations will get re-queued in a way so that it is safe to retry them. Running the same operation twice should not cause duplicate edits or, let's say, double commits. And this pattern came from CI pipelines, which would fail partway through and would leave the code base in a broken state. Now you notice the pattern here, right? None of these were designed upfront. Each of them were added after a real production failure, right? And that's the honest truth about reliability engineering. You don't know what will break until it breaks, right? And that's our design decision 10. Every reliability mechanism has some kind of a postmortem behind it. So design defensively, yeah. Now this brings us to part 7, which is about memory and context. And I believe this is one of the most important parts. So we have several kinds of memory. Do you remember earlier we talked that model has no memory of its own. Every turn it starts from scratch, right? So the system has to provide memory for it, and not just one kind. So Claude Code uses these 4 distinct memory tiers, each with their own scope and some kind of a different storage backend, right? So this is your working memory. So what is the scope here? The scope is this particular turn only, right? This is everything currently inside the model's context window, right? The conversation that you had so far, the tool results, the system prompt. So it's like the model's RAM, right? When the turn ends, a new one begins, and it gets rebuilt from scratch. Now it's fast, but it's very expensive. Every token is going to cost you money. The second kind of a memory is the session memory. What is the scope of the session memory? It's this entire conversation that you're having, the multi-turn conversation. So when you close your terminal and come back later, the conversation picks up from where you left off. Now that's because the full conversation log, your every message, every tool result, every checkpoint is saved to some kind of a disk, right? The model does not remember it, right? But the system reloads it into the context window when you resume the session. Then you have the project memory. The scope of this memory is your repository. Now, this is your claude.md file, the markdown file that gets committed to Git alongside your source code. It contains project-specific instructions, architecture decisions, coding conventions, right? Like don't touch this file, or the preferred libraries that you want to use. So it gets loaded once at the start of every session. So the model always knows the rules of your project. Now, because it is in Git, your whole team shares the same project memory, right? And then you have your tool result memory. So what is the scope of this memory? It is the big outputs, right? So when a tool produces a result that is too big to keep in the context window, let's say a 50,000 characters log dump, the full output gets saved to a file on the disk, right? So only a small preview will stay in the conversation, and the model can reference the full output if it needs to, so that it does not clog up the context window. Now you notice this, every tier here is in its exact place where it needs to be. Working memory is in the prompt. It is fast, but ephemeral. Session memory is on the disk, character log dumps, and etc. Right? So sorry, session memory is where you persist your entire conversation, and it can restart from where you left off. Then you have your project memory, which is in the Git, which is shared across the team, and the tool result, which is for it could be in your temporary files, right? Where you have like large outputs. And this is our design decision 11. 4 memory layers, different scopes, and each lives in its right place, right? Okay, let's quickly talk about the token budget. And this is very interesting. So let's look at this diagram here, right? Let's say you have this 200K token budget. Now, where those 200K token actually go, this is important to know, right? So you would think 200K tokens is a lot of space, but before the user even types their first message, a big chunk is already spoken for. And that's what we're looking at right now. So you have your system prompt, which is about 2,700 tokens. This is the core set of instructions that tells the model how to behave. Things like your Claude Code, follow these rules. Here's how you will use the tools, and this gets cached globally, which means that it's the same for every user and every session. So you only pay for it once, right? Then you have tool definitions, right? So this is about 17K tokens. This is the schema for all the 50 plus built-in tools: read file, edit file, bash, grep, and everything else, right? Now, each tool needs its name, description, input parameters, type definitions, and which gets sent to the model so that it knows what tools it can call and how to call them. So 50 tools, it's going to add up really fast, right? Auto compact reservation, right? So this is about 33K tokens. So this is the space which the system keeps off limits as a buffer. Why? Because when the context window fills up, the system needs room to run compaction, which is summarizing the old conversations to free up some space. So if you fill the window to 100%, there would be no room left to even run the compaction process. So this reserve is like keeping your petrol tank above empty. So so you need fuel so that you want to go to the petrol station, right? Now that leaves about 147K tokens of free working memory, which is only 74% of the total 200K window. So you started with a 200K budget and you have already spent a quarter of it before the user types even a single character. And that's why every token matters, right? And that's why compression, caching, compaction, and all of eviction, they are not nice to have. They are really the survival mechanisms here, right? Okay, let's talk about the compression strategy. So what happens when that 147K of free space starts running out? What do you do? So you compress, but not all compression is going to be equal. Some compression methods would be free. Some would cost you some kind of a money, right? Some may lose information as well, right? So Claude Code, it stacks these different compression techniques into layers, right? And the cheapest ones will fire first. So if you're trying to do some compaction, you'll first start with the cheapest one. And if it doesn't suit your needs, then only you go for the one which will cost more. So the first one is you persist the tool results to disk. Really, the cost is zero here. You're not making any API calls. So if a tool returned a huge output, like your log dump, you will move the full result to a file on the disk and just leave a small preview in the conversation, right? So this is the same tool result persistence which we covered in the self-healing before, right? So it frees up the context window without making any API calls and without losing any data. The full output is still on the disk if the model needs it later, right? Then history snip, right? So here again, the cost is zero because what you're really literally doing here, you're dropping the oldest turns from your conversation. So the idea is very simple. If the conversation is 40 turns long, the first few turns are probably not relevant anymore. Snip them, right? No API call needed. Just stop including them. Now, what is the risk here? The risk is if something from turn 3 is still important at turn 40, it's gone, right? Then you would, the third strategy is of micro compaction. Again, here the cost is zero. So this is like a lightweight local compression where you do things like removing duplicate white space, trimming the redundant tool metadata, or you collapse the repeated system messages, right? These are small savings individually, but they add up across a long conversation. So no API call, no information loss on the content, which actually matters for the model. Now, the layer 4 here is something called context collapse. Again, here the cost is zero because you're not making API calls, but this is more aggressive than micro compact here. So instead of trimming white spaces or metadata, it collapses the entire blocks of older conversation into shorter representations using some heuristic rules, not actually a LLM call. So just some pattern-based reduction. So for example, if the model, let's say, read a file 10 turns ago and then edited the same file 3 turns ago, the older read result can be collapsed down to just the current whatever whatever reading you have done, right? Because the edit already has superseded it. Or if, let's say, there were 5 consecutive tool calls which all succeeded, then you collapse them into a single summary line instead of keeping all the 5 full results. So the key difference here is that from a fork summary, that here no models involved really, right? These are some kind of a mechanical rules. So they are fast and free, but they can't judge what's actually important the way a LLM model can judge, right? Now, the last one is fork summary, right? So here you're going to make an API call. You're going to call the LLM. And this is the most expensive option and also the highest quality here. The system sends the conversation to the model and asks it to produce the condensed summary. So the summary is going to replace the old conversation history. It is going to cost you real money because you are making an extra API call to the LLM. But the summary retains the most important context because the model actually understands what matters. So here, the pattern is clear. Try the free options first and only pay for compression when the free methods are not enough, right? Each layer down the stack gives you better fidelity, but is going to cost more. And every lossy step, let's say from history snip through this fork summary, that risks losing context that might matter later. So this is the trade-off here. And this is our design decision 12. Try free options first and reserve the expensive options when you genuinely need them, right? Okay. Now, when we think about compaction, right? Compaction of the conversation, complete conversation in your context window, it's actually not just about throwing stuff away. If all you did was delete old conversation to free up space, the model might lose critical context. It would forget what files it is working on, or what the original plan was, or what the project rules it has to follow. So compaction is actually 2 operations that must happen together as an atomic operation, as an atomic transaction, which is eviction, plus rehydration, right? Now let's quickly walk through this. So before compaction, the context window is, let's say, at 190 key tokens, almost 95% full. Now the conversation is cluttered with old tool results, which the model probably no longer needs. Some stale file references from files that have been edited since they were first read. Maybe some duplicated MCP instructions that got re-injected multiple times. So now the compaction fires. First, it evicts. It removes all the stale, redundant, or outdated content. But then it also immediately rehydrates, right? It puts back the things the model actually needs going forward, right? So now, if you look at this before and after diagram here, let's say the 5 most recent files get re-injected, because those are the files the model is actively working on right now. If you evicted everything and did not put these back, the model would have to reread them, which would waste time and also your tool calls. Then your active skills, right? They get reattached. If the user has loaded, let's say, some kind of a skill prompt, like a coding style guide or a domain specific instruction, those get put back in the model. And so that the model can keep following them. Your claude.md, right? It gets reloaded from the disk. This is your project memory file, the one you have checked in the Git. So it might have been updated since the session started. Maybe your teammate committed something new, some new conventions. So the system reads the latest version from the disk, not any stale copy that is in the conversation, right? And then plan and sub agent state gets restored. Now imagine the model is halfway through a 10-step refactoring plan. It has completed steps 1 to 6, and it knows steps 7 through 10 are still pending. Now, if compaction evicts that plan, the model has no idea where it left off. It might redo the work it has already finished, or maybe skip the steps entirely, right? And same thing is true with sub-agents. If the main agent dispatched the sub-agent to explore the code base and got back a summary of findings, that summary needs to survive compaction. Otherwise, the model would just redispatch the same sub-agent, right? And would burn tokens. Then you have this prompt cache prefix kept. This is something that I want to take a moment to talk about in a little more detail, which will come on the next slide. So you remember the tool, the system prompt and tool definitions, which from the token budget that we spoke about. So those take up about 20,000 tokens combined, and they are identical for every turn, right? So Anthropic's APIs lets you cache that prefix so that you don't pay full price to resend it every time. And here's the catch. So if the compaction rearranges the beginning of the prompt, even slightly, the cache key is going to change and it will result in a cache miss, which means that you would pay full price for all those 20,000 tokens all over again. So compaction is carefully designed to only modify the conversation portion of the prompt, and the part of the cache prefix is left untouched. So we'll go deeper on it in the next slide. So after compaction, about 50K tokens are free, let's say, and the model has everything it needs to keep working, and your cache is still warm, and the whole operation will look seamless to the user. They don't even know what has happened really. So this has to be one transaction. Evict now and rehydrate later is not going to work. It has to be done as a one transaction. And that is our design decision 13. Eviction plus rehydration is one transaction, and you have to design them together. This prompt cache prefix, I'll just quickly cover this slide, and you'll understand what I'm talking about. So every time Claude Code sends a request to the Anthropic API, it sends the full prompt, the system instructions, tool definitions, conversation history, everything. And that's expensive. But Anthropic's API supports something called prompt caching, which means that if the beginning of your prompt is identical to a previous request, the API recognizes it and charges you, let's say, about 1/10 the normal price for those cache tokens, which is almost 10x cost reduction. So the trick is you split your prompt into two halves, right? There's a boundary in your prompt. On the left side is your static prefix. This includes the core system instructions like your Claude Code, here are your rules, and all the tool definitions. So this content is identical for every user, every session, every turn. It never changes, right? That's what makes it cacheable. The API is going to see this prefix over and over and will serve it from the cache. On the right-hand side is the dynamic stuff. This is everything that's going to vary. The user's conversation history, MCP specific instructions from whatever external tools they have connected to, their output preferences, right? And all of that. So this part changes every turn, so it cannot be cached. So you will pay the full price for it every time. And the key constraint here is that you never let the dynamic content leak into the static prefix. If a single user specific token ends up in the prefix, let's say an MCP instruction gets accidentally placed before the tool definitions, the cache key is going to change for that user, and every request then is going to want them to pay full price for the entire prefix, which will increase the cost. So this is our design decision 14. Static prefix cached, dynamic suffix gets charged every request, and this reduces some cost. Now I'll hand over to IK to let you know a little more about how to be a 10x developer, 10x professional with IK, and then we'll come back and talk about the other 8 design decisions that we still want to take to finish the system design of Claude Code. Over to you, Moin.
Yes. Thanks, Yuvendra. Hi guys, Niyati here. Yuvendra, firstly, thanks. It's been a super engaging, session, and we are going in. God is in the details, so we are going in as much details as we can. I know time is not a friend today, but so guys, we will extend the session a little bit. But I can already see a lot of interest from you guys. Now I'm here to. I'll tell you why am I taking this the next 5-7 minutes only, and then quickly hand it over to Jivendra back. That A lot of you, when I went through the results of the poll that we did in the beginning, and Moin must have taken you guys through that poll, a lot of you guys said that currently where you're stuck is that you're not able to get through interviews because you don't have the right AI skills. About 49% of you said that you don't have a structured program or a structured approach that works. The good thing is we know a structured approach that works. Any of you at this point of time would be in any of these 4 quadrants or the 4 boxes that you can see in front of you. You may feel that AI is either moving too fast, or maybe your role is, too unique and too safe, or you feel that there's so much out there, I don't know where to start from. And, maybe that's why you're starting by at least joining these master classes, which is well appreciated, firstly. Or you feel that, I have about, we mostly, our audiences are experienced tech professionals. So you feel that I have 10 years, 8 years, 15 years, 20 years of work X. Like, how am I going to start from scratch? You actually don't have to start from scratch. So that's the first myth I want to burst. Okay. To tell you about the journey of this AI era that we have seen till now, earlier, about 2-3 years back, we were generally working in the augmentation sector, which was increasing our own productivity with the help of AI. So using LLMs to sort of be our assistant while we are working, or co-pilots, right? So increasing our productivity in general work. But now we are in that transformation phase, and that's why most of the roles, all of the roles, that are present, tech roles that are present in the Indian market at this point of time, and companies that are hiring for, they are asking for this kind of skill. So either you could layer your current tech stack, so you don't have to start from scratch. You can currently layer your tech stack with the right AI skills for your role. Okay. And I'll tell you how, we can customize it for you. Or you can tweak the current models, build on top of the existing models, or you can actually just, go ahead and build your own modern ML models, right? So how do you do the first thing? Most of our learners fall in this bracket, which is, I think, in the poll also we asked that what is that one thing you're scared of, or in a way try to ask that, and you said that I want to layer my current tech stack with AI skills. I don't want to start from scratch. I have enough tech knowledge. So we have the right programs. So in the interest of time, I'll directly jump to the programs. So if you're looking to layer your current tech stack with the right AI skills for yourself, then we customize that track for 18 different tech domains. That means if you're a backend engineer or a full stack engineer or a technical program manager or an engineering manager, heading an engineering team, you all will have different AI paths, okay, and interview paths. So our all our programs are a combination of upskilling plus, because we are outcome oriented, also we cover the interview preparation part. I'll quickly take you through what that means. So in the AI upskilling bit, which is the agentic transformative Gen AI and agentic AI interview lab, this particular program, over here for your role, what projects, what concepts are relevant from an AI standpoint, we teach you that. And we also have three versions of it: pro code, low code, and no code. So developers, they generally take pro code as they're proficient in coding, and no code for people with tech professionals who do not generally code in a day-to-day basis, or low code, say for a data analyst who wants to go ahead and take that version of the program, that is also available. Projects are also going to be customized, and your interview preparation path, that is also going to be customized. So you'll actually be sitting with and each of our interview preparation paths, they have 15 mock interviews where you will be sitting across experts like Jivendra, who hire for their companies, hire people like you, and they are going to give you real-time feedback, written and verbal feedback on how is your person. There are 15 chances to perfect your interview prep, and that comes with across of our programs. The second program that we offer is with PwC India. So the certification is provided by PwC India and Interview Kickstart, which is if you are proficient, fairly proficient in the AI, AI upskilling path, then we help you build a portfolio. So there are four enterprise grade projects that you can build and use that portfolio to crack interviews ahead. This also comes with the interview prep lab, again customized for 18 roles. The last is if you want to switch and completely become an ML-led tech professional. For example, from an software engineer, you want to move to a machine learning engineer. This is a program for you, which is called Flagship Machine Learning and Interview Prep Lab. Okay, so over here we cover obviously concepts of ML from scratch, but we also cover concepts of Gen AI and agentic AI along with the interview preparation. In terms of timeline, the first, if you're unsure, firstly, of you don't know where to start, then first thing and the most essential thing at this point of time, I believe, is the fact that you have to add the right AI skills to your current tech stack. Go ahead, do that. Okay. This is where bulk of the AI jobs are right now. All of the JDs that you must be going through, and this is not something that's coming from me, it's coming from all the JDs that we are seeing around. They are asking for AI skills in your domain, whatever domain you are from. So that's about 3 months of upskilling, 3 months of interview preparation. The PwC program is 12 weeks of portfolio building and 3 months of interview preparation. And the flagship machine learning program, which includes agentic AI, is 6 months of upskilling and 4 months of interview preparation. Okay, these are the pricing in front of you. They are based on the domain that you come from. We have currently some scholarship offers that we are running, and we also have EMI options. We have loan partners that can help you. So all of our, by the way, we have about 27,000 plus student base by now. You must have heard from Moin. We have been doing this for 12 years now. All of our learners are working professionals with families, responsibilities, and everything. So we do understand that, and therefore we help you break it down through EMIs and through our loan partners, get that assistance. We are also tied up with about 200 plus hiring companies. So if you successfully complete the program, we can refer your profile whenever we see a suitable opening. What was interview preparation? Like I said, I've covered this part. It's customized for whatever roles you see in front of you. It's actually customized for each of these roles. So we don't believe in straight-jacketed approach. That is where the moat comes in, where you realize that what you are understanding is particularly built for you. It's not that every tech professional sits in the same class and gets the same knowledge. So I took you through this already, that in interview preparation, we'll take you through 15 mock interviews minimum. We'll help you with resume, LinkedIn optimization. We'll take you through behavioral salary coaching, and in the lessons and in the modules, we'll take you through DSA concepts, system design concepts, and particular interview modules for you. So if you're a front-end engineer, your modules will be interview modules will be very different from someone, say, like a product manager, right? For EMs, we have special leadership modules also. So that's what we offer. And we wanted to take a break and tell you about this. And I'm going to stop sharing and quickly hand it over to Jivendra. But why we wanted to tell you this is because a lot of you have asked this particular question on, I want a structured program. 49% of you, as I said. I'm going to launch a poll to understand how many of you want to hear back from us. And just take you through what's changing in your domain. How is AI changing your domain? What's happening? What kind of roles are coming? And if you're actually targeting to get a job this year, this becomes an essential point to start. So I'll leave it at that. I'll leave also the calendar link of our program expert, whom you can book a calendar with as per your convenience. And go ahead, just have a chat with us, and we'll take it from there. Thanks. Thank you, Vinder. Over to you. Jivendra, you're on mute.
Am I audible now?
Yes.
Okay, thanks, Niyati. So this brings us to the eighth part, which is the model API layer, or the actual LLM, right? So let's actually go to the next slide and then let me. Okay, all right. So we need to decide the tool protocol, right? When the model decides that it needs a tool, let's say read file, how does it actually communicate that request? And there are different ways to do it. And this choice is going to have some consequences if you want to stream the tokens, or if you want to port this particular Claude Code to any other operating system. So there are these different options, and all of them are equally valid, but they have their own pros and cons. The first one is the JSON mode, where the model is going to output a raw JSON text in its response, and the agent or Claude Code or the system parses it. So for example, the model might literally output the text tool read file path author.py, right? Like a JSON as part of its response. And then the Claude Code has to find that JSON, extract it, and figure out if it's a tool call. Now, what is the upside of it? The pros of it? It is provider agnostic. Any model can output text, and so it is going to work with any provider. But the cons, obviously, a lot. It's brittle. The model may output malformed JSON. It's not models are non-deterministic, right? It can output malformed JSON, and the whole call fails. There is no streaming, right? You have to wait for that entire response before you can parse the JSON. There's no retry semantics, no built-in way for the API to tell you that, hey, this is a tool call versus this is a regular text, and no structured way to report the results back. Another way would be the function calling. This is the approach OpenAI has popularized. And if you have used frameworks like LangChain, you must have used this before. Here, the model's response explicitly marks that, hey, this is a function call as a structured output, which is separate from your usual text responses. It's much better than JSON because the API itself tells you this is a function call, here's the name, here's the arguments. And it has become the industry standard. But the con here is that every provider implements it slightly differently. So it's not one protocol. It's like a family of per provider variants. Then the third one is the tool use, which is native to Anthropic. This is Anthropic's first-class primitive designed from ground up for tool invocation. So when the model wants to call a tool, the API returns a structured tool use content block, right, as a part of the response itself, alongside your usual text blocks. So it has a tool name, the input parameters, a unique ID, and all of them type checked and validated by the API server before it even reaches your code, right? Streaming is built around the content blocks, So you see the tool call forming token by token as it generates. And when the tool finishes, you send back a tool result block paired to that same ID with success or failure, whatever, and the model knows exactly what happened. Now, the downside of it is that it locks this whole shape to Anthropic AI. So if you wanted to swap providers, you would need to rewrite this layer. So the question is, if function calling already works, and it does, why would Claude Code choose tool use and accept this kind of a lock-in? Because Anthropic built both the model and the API. So the tool protocol is designed to work perfectly with the Claude's architecture, right? The streaming format matches how Claude generates content. The validation matches how Claude, it is going to match the Claude's output patterns, right? Everything is native here. So it's like a home field advantage, right? When you own the entire stack, the model, the API, and the product, using a generic protocol means you are paying some kind of a abstraction cost for the portability that you really don't need because you own everything, right? It's your monopoly. So this is our design decision 15. If we were Anthropic, then we would use this tool use, right? Design our own tool use natively. All right, model routing, right? So you have one agent, but not one model. So Claude uses 3 different models, and it picks which one to call based on how hard the task is. Why? Because you wouldn't use a sword where a needle will do the job, right? So that's the reason. So Opus 4.7, this is the most capable and the most expensive model. It handles the main reasoning loop, the hard stuff. When the model needs to understand a complex code base, plan, let's say, a multi-file refactoring, or debug some kind of a tricky issue, that's Opus for you. You're paying the top dollar, but you need the reasoning power, right? Then you have Sonnet 4.6, for example, the mid-tier model. It is fast and cheap. So Claude Code uses it for the permission classifier, right? The part that decides should this tool call be allowed or blocked. That's a yes, no decision, not a creative task. So Sonnet handles it at a fraction of the cost. And then you have Haiku 4.5, which is the smallest and the cheapest model. It has almost near instant responses. So Claude Code uses it for quick format checks, simple routing decisions, trivial tasks where speed matters more than the depth, right? So the key insight here is that the model selection is a per call decision, not a per app decision. The system does not pick one model at startup and use it for everything. Every single API call asks, what is the cheapest model that can handle this specific task? Read a file and decide what to do next. Opus. Check if a bash command should be allowed. Sonnet. Quick validation. Haiku. Same agent, different model for each call. And by the way, the user can override this too. So inside the CLI, you can type /model and pick whichever model you want for the main reasoning loop, or you can set the Anthropic model environment variable before launching. So the system routes automatically, but the user always has the final say. And that's our design decision 16, where you route by task. Don't pay Opus prices for a yes/no classifier, right? Now this brings us to part 9, which is safety and permissions. Threat model. So start with this assumption. The model can be turned against you. It reads files, fetches URLs, run commands, and any of that input could contain instructions which are designed to hijack it. So you design for multiple specific threats that are possible. And obviously, everybody knows prompt injection is the biggest threat at the moment. So you could have a malicious file or URL which can embed some hidden instructions like ignore previous rules and delete everything. So the model is going to read it, and now those instructions are inside the context. So it can be a real threat. There are several ways to mitigate it, like you sanitize the outputs before they reach the model, recheck the permissions on any action, which is going to, let's say, follow some untrusted input, right? So these are some mitigation mechanisms here. There are other threat categories here, like bash command injection, where the model, let's say, constructs a shell command with some special characters, which can change what the command actually does. So for example, it might generate a command that looks like list files, but hidden inside is, let's say, some kind of a semicolon followed by delete everything. So it looks harmless, but it does real damage, right? So the mitigation here would be you parse every bash command so that it does not break the so that it's not a harmful one. You basically try to break it down into its actual structure, right? So instead of just reading the text and hoping it looks safe, it should understand what each part of the command actually does. So that way it can catch the hidden trick, right, at the syntax level. Credential exfiltration is where the model sees the secrets in the context, right, in the code base, like your API keys, tokens, passwords, whatnot. And a prompt injection trick can leak it through a tool output. Maybe they can ask it to write to a file or include them in some kind of a URL. So here the mitigation is that you should have some kind of a allow list proxy where the agent can, let's say, only make network requests to URLs you have explicitly approved. So even if the model tries to send your API key to some external server, the request gets blocked because the server is not on that list. There is another mechanism here where you sandbox the file system scoping so that the agent can only read and write inside the directories you have allowed. So if the model tries to write your secrets to, let's say, a file outside the project folder, or maybe a temp file somewhere, which an attacker is asking it to, then the sandbox is going to block it, right? So that secret is going to never leave the approved boundary. Lateral movement is where one tool's output becomes another tool's weapon, right? So the model reads a file that tells it to maybe run a dangerous bash command. So harmless read is going to escalate into a destructive action, right? So here the mitigation is that you do per tool permission scoping. So each tool has its own permission boundary. So a read result cannot automatically authorize a write or an execute, right? Denial bypass is where let's say the user says no to a dangerous command. So the model rephrases it and tries again, hoping to slip past the check. So here mitigation is that you do denial as a tool result. So when the user says no, the denial is recorded as a permanent part of the conversation, and the model sees it, and the audit trail is going to preserve it. So the closing thought here is that closing thought is that behavioral safety is telling the model don't do bad things, but that is always fragile. But if you have structural safety, where you are parsing commands, scoping permissions, sandboxing things at kernel level, that is something that will actually hold, right? So permission cascade, yeah. So this is that permission pipeline that I spoke about earlier, which we wanted to get into a little more detail. And there were questions I saw on permissions. So here in permission cascading, we stop and give the answer as early and as cheaply as possible. We do not want to escalate to an expensive check for a tool call if a cheap one already has the answer, right? So these are different stages here, right? So here, let's say the tool call arrives. The first you have static rules, which is like a hard-coded table, right? With allow or ask or write, things like that, right? So if you want to read a file, that's always allowed. If you want to run a bash command, it needs to be asked, right? So it's simple as that. Very static rules. Most calls will get their answers right here. Most tools calls will get their answer here. If it does not work, right? And here the latency is also very minimal, right? It's order of microseconds. Even if this one fails, then you go to tool check permission, right? Where the tool itself refines the decision. So if it's a bash, then it gets its command parsed for danger. If let's say there is like a file operation, you get the path checked. For example, is the file inside the current directory or not, or inside the allowed directory or not, right? That's what this tool check permission is. Then you have permission mode. So here the latency could be order of milliseconds. Like what mode is the user in, right? Are they in the accept edits mode, which lets the file edits sail through, or they are in the plan mode, where everything is read only and you cannot write anything, right? Even if this layer also fails, then finally you go to LLM classifier, where the latency is order of, again, few hundred milliseconds. And this is going to only fire in the auto mode, where Sonnet looks at the tool call and classifies it, whether it is safe or not safe. It's one of the most expensive automated check. That's why it's down here, not in the stage one. And finally, you have ask the human time. If nothing above this could decide, then you show the user a yes, no prompt and wait. Now, eventually, the Anthropic claims that 93% of prompts that reach the human are approved. Humans approve it, right? Because this cascading has filtered the noise. And this is from Anthropic's own auto mode blog, right? So this is our final 17th decision. Deny wins. You do keep checks first, and then if everything fails, then only you ask human to approve it. And 93% approval proves that the cascade is filtering things really well here, right? I'm sure most of you who have used Claude Code, you must have run it in auto mode, and then there are debates that whether it should be run in auto mode or not, because when you are using Claude Code, you must have seen a lot of issues that are coming up. Like, for example, there's something called context anxiety, where when the context window is about to get full, Claude Code just responds in very irrational ways. It might start saying things like, hey, we have done enough for today. Do you want to do it another day? So it starts doing things like that. So yeah, those are some other problems that you might have encountered. Okay, kernel sandboxing is an important thing that we want to talk about. This is the permission cascade we have covered in software, right? Where it's code that is making decisions. But what if the code has a bug, right? What if a prompt injection that tricks the model into bypassing a check? So you would need a second line of defense that does not depend on the application logic at all, right? That's where the operating system's kernel comes in. So on Mac OS, the Claude uses something called a seatbelt, which is Apple's built-in kernel sandbox framework. It tells the operating system itself that this process is only allowed to access these directories and these network endpoints. The application cannot override it. The model cannot talk its way out of it, right? The kernel is going to enforce it. Then on Linux and Windows side, it uses something called a bubble wrap, which is a tool that creates isolated environments using Linux namespaces, which is the same technology that powers Docker containers also. And on top of that, there is a allow list proxy, which controls to maintain an allow list of which network addresses the agent can reach, and only the approved URLs will get through. And what is the result of the kernel sandboxing? That 84% fewer permissions prompts with sandboxing enabled, right? And this is a verified number from Anthropic Sandbox blog. The user gets asked less because the kernel is already blocking the dangerous stuff silently behind the scenes. But there's a catch here, right? Which is also called as the escape hatch problem here. So the model has learned that when a command fails inside the sandbox, it can retry with a flag like dangerously skip permissions, right? So how does it know that? Because it has figured this out from the training data. So the model is actively trying to turn off the safety layer. And to close this loophole, you would have to explicitly set this allow unsandbox commands to false in your configuration. Otherwise, the model can talk itself out of the sandbox. And this is our design decision 18. Behavioral safety rails fail, right? The model will try to work around it. but the kernel does not negotiate. So we will use OS sandboxing as the final floor, right? Okay, now the 6 permission modes. Think of it like a trust dial, right? 6 settings from maximum caution to maximum speed, right? So the default here is that you ask before every action. So every tool call gets a yes, no prompt. It is safe, but very slow, right? This is what probably the new users would start with. And then you have accept edits, where the file edits are auto-approved, but bash commands will still get asked. So good for you when you trust the model's code changes, but want to review the shell commands. Then you have plan mode, which is a read-only mode, where the model can read the files and search the code base, but it cannot edit or run anything. It plans what it would do and shows you, but takes no action. So it is useful for reviewing what the agent intends before you let it loose in your code base, right? And then you have the auto mode where the LLM classifier decides. So recall that stage 4 on the permission cascade. So in this mode, Sonnet model is going to evaluate each tool call and approve or block it automatically. So the human will only get asked when the Sonnet model is not sure. Then don't ask, right? Which is allow listed, where allow listed commands run silently. So if a command matches the allow list, it executes without you asking. Everything else still will get checked with you. A bypass, where you skip all permission checks, maximum speed, right? And minimum safety. But even bypass has that floor, right? It still blocks, let's say, writes to .git, .clode, .claude, .vs code directories, right? So those are protected no matter what. So there's no setting that can turn off everything, but this is like the one with minimum safety. So the design decision 19 here now is that let the user pick their risk tolerance, but you really never give them an off switch for everything, right? So this is our design decision 19. Now this brings us to the 10th section, which is about extensibility. You must have been hearing about skills a lot these days, that going forward, most of the tasks that we are doing in software, they should be some kind of a skill, right? So that's where extensibility comes into picture. So here, how do teams make Claude Code work their way without changing the source code, right? So these are different customization surfaces which have different scopes here, hooks, skills, and whatnot. So hooks are the scripts that run automatically before or every tool call. So you have 2 types here. One is your pre-tool use, which runs before the tool executes. And then you have post-tool use, which runs after. What can you do with them? You can block certain actions, like preventing edits to some, let's say, a protected directory, or modify inputs like rewriting the file paths to follow a naming convention. You can do some auditing, like you can log every bash command to some kind of a compliance file, right? And then do a bunch of stuff like that. So the key thing is here that hooks are your code, which are running in your environment. Claude Code just calls them at the right time. Then you have skills, right? This is the most important component these days now. Skills are like reusable instructions that you load in the model's context. So think of them as like cheat sheets, right? For example, you say use single quotes, tabs, not spaces. All API responses must include a correlation ID, right? And stuff like that. So you basically saying that you have to always follow a certain convention. And not just that. With a skill file, you can actually automate a lot of your workflows as well, right? So if there are some repetitive tasks that you do, you can simply write a skills.md, which is a natural language file, and it can Claude Code can use it and run your workflows, right? And then you have your Claude.md, this one, which is the project memory file that we talked about earlier. It lives in your Git repo right alongside the source code. it gets loaded once at the start of every session. Your architecture decisions, coding conventions, and whatnot, right? Anything the model needs to know about your specific project, because it's in Git, so every developer on the team sees the same rules. So all these three, they work behind the scenes. The model does not know they exist. It just sees the effect, right? Better behavior, consistent style, project-aware responses, and because none of them require changing the Claude Code's source code, so a team can customize everything without maintaining their own version of the product, right? And that's your design decision 20. 3 customization surfaces, 3 different scopes here, and you don't need to fork, right? Subagents, right? So subagents, sometimes the main agent needs help, right? Everybody needs help. Say it's working on, let's say, a large refactoring task, and it needs to explore 50, 100, whatnot files to understand the code base, and then plan the changes and then implement them. So doing all of that in one context window means the conversation obviously gets enormous, and eventually you hit the context limit. Sub-agents solve this. So you recall earlier in the session, I said that Claude Code is a single main loop, not a multi-agent graph. That hasn't changed here. A sub-agent is just another tool call. The main loop dispatches it. In the same way, it dispatches a read file or a bash command, right? It's the same model, the same Claude running through the same pipeline. The difference is that this tool call gets its own fresh context window, a clean slate, with its own system prompt and its own restricted set of tools. So think of it like sending a copy of yourself to go do some kind of a specific task and come back with a summary. So when the sub-agent finishes, only the final summary comes back to the parent, not the full conversation, not every file it read, just the conclusion, right? So this keeps the parent context clean. So there is a constraint here, though. You can run about up to 10 sub-agents at the same time before the system will start queuing them, right? And very important, sub-agents cannot spawn their own sub-agent. It's a single level only, right? There is no nesting here. And it's a deliberate limit to keep things simple and debuggable. Now, the trade-off is very clear here. Sub-agents give you about 90% performance improvement on complex tasks. This is what Anthropic claims, but they obviously cost you a lot, sometimes 15x the token cost, because each one is going to run its own full conversation with the model. So you don't use them for everything. You use them when the task is too big for one context window, or when you need let's say, the isolation of a separate workspace. So this is our design decision 21. Sub-agents are an isolation tool, not an orchestration framework, right? So use them only when isolation matters. Out of 22 design decisions, we have covered 21, one more to go. MCP and external tools. Okay, so far we have talked about tools like read file, edit file, grep, bash, whatnot. All of that is built into Claude Code. But what if you want to connect it to external services like GitHub or Slack or Postgres, your company's internal APIs? That's what MCP does. MCP stands for Model Context Protocol. It's an open protocol that lets you plug external tools into Claude Code without writing custom integrations. So Claude Code sits at the center like a hub, and each MCP server here is a spoke connection to a different service, right? Now, the problem here is that every tool the model can use needs its full schema loaded into the context window, right? So you remember the model has to see the tool definitions to know what it can call. And MCP tools are no different. Without any optimization, let's say if you're connecting to 30 MCP servers, it's going to take about 134K tokens, right, of tool definitions before the user even types a single character. In fact, GitHub's MCP alone would take up 24% of the context window. So what is the fix here? The fix here is lazy loading, right? It can also it's also called as deferred loading. So instead of dumping every tool's full schema into the context upfront, the system only loads the tool names, like short labels, right? No details really. So when the model actually needs a specific tool, it is going to call a tool search, right? Which is like a lookup, a lightweight lookup, and only then it loads the full schema into the context, whatever tool it needs, right? And obviously, the savings are going to be very dramatic here because if you have like 30 servers, then and you load all the tool schema and results and every tool schema and descriptions and everything, that's 134K tokens. But if you just load one, then probably you'll be doing some 5K tokens, which is 85% context reduction, right? And this is our design decision too, where you use MCP with deferred loading, load the tool names eagerly, and load the full schemas lazily, right? So this is the same idea as dynamic linking in operating systems, right? Where you load the capability list at the startup, but only load the actual code when it's called. So recall your operating system class, and you'll remember this concept. Right, now this brings us to the part 11, which is about the UX, the state of the UX, the streaming and stuff like that. Here, let's think about the latency budgets here. So why does latency matter for a coding agent? Because if the agent feels slow, developers are going to stop using it, and they might go back to doing things manually, which I think is very highly unlikely, but still that is possible. So these are some of the targets, right? The time to first token should be under 500 milliseconds. Token streaming rate should be 20 to 30 per second. Simple tasks with calling one tool should be under 5 seconds and stuff like that. But the key insight here is that these are not nice to have targets, right? They drive real architecture decisions. The custom TUI that we spoke about earlier, the parallel tool calls, model routing, all of that is because we want to achieve these targets, right? Again, Claude Code can work in completely different modes. It can work in interactive mode and headless mode, where you have the same agent loop, same tools, same model, but two opposite user experiences, right? Now, in case of interactive mode, this is what you already know, where a developer is sitting at the terminal, typing in real time. And in this mode, the system streams tokens to the screen as they're arriving. It shows the live progress for each tool call, presents a yes/no prompt whenever a permission decision is needed, right? And user can interrupt with Control-C or rewind with pressing escape twice, right? So everything is designed around a human watching and reacting. And in the headless mode, nobody's at the keyboard. Claude Code is running inside a CI pipeline, let's say GitHub Actions, right? Or triggered by Slack command, right? So there is no one to click yes on a permission prompt. So the system has to decide on its own, either auto approve based on the permission mode and allow list, or fail the operation entirely, right? No streaming. The output is a batch JSON that the CI system can parse. There would be exit codes that are deterministic. Exit code 0 means success, non-zero means failure. So the pipeline knows what has happened. Retry should be idempotent, right? Same operation should not run twice and cause duplicates, right? So how does one agent loop serve both experiences without writing duplicate code? And the bridge obviously is event bus here, right? If you understand what event-based programming is, you would immediately get this, right? So same event, you will have events being sent to event bus, and there would be different listeners, right? That's the whole trick. The agent loop stays the same for both modes. It does not have like a if statement that, hey, if I'm in interactive mode or a headless mode, then do this or do that, right? It just broadcasts and the surface handles the rest, right? So If tomorrow, let's say you wanted to add a third surface, let's say a web dashboard or some other bot, you don't need to touch the agent loop at all. You just write a new listener that subscribes to the same events and returns them however the surface needs, right? The agent loop does not need to change. Right. Now, finally, we want to talk about the last section of today, which is evaluation and observability. So, yeah. So, how do you test a system that gives a different answer every time? Remember the non-deterministic outputs, right? Which means the same input can produce different but valid results. So you cannot write a traditional unit test that says expect this exact output. So you need a different approach. And the evaluation pipeline works like this. You maintain a frozen test suite, a fixed set of tasks with their known correct outcomes. And before shipping a model upgrade, you run every task through the new model and compare the results against some kind of a baseline so that the results from the previous model version, right, you compare it against them. If the new results are as good or better, you ship. If they're worse, then you roll back, right? So think of it like a before and after comparison, right? Not like a pass or fail test. So there are different types of evaluation here, right? You want to evaluate the task completion. Does the agent actually finish multi-step tasks? Like give it a bug to fix, a feature to implement, some refactoring to do. Did it get to the end, right? So this runs at every release of the model. Tool selection. So does the agent pick the right tool for the job? So when it needs to find a function, does it use grep or does it wastefully read every file one by one? Picking the wrong tool might work, but it would waste time and tokens, right? So this is also something that will run every release whenever you're making any changes to your Claude Code system. Permission accuracy. Your auto classifier, right? Where the Sonnet model decides whether it is safe or not to run a tool. Agree with what the human would have decided, right? So if the classifier is approving things which the human would block, then that's a safety gap, right? If it's blocking things the human would approve, that's a friction problem. So this is something that also runs, this evaluation also runs continuously. Then your latency, right? Whether the P50 and P90 numbers, how are they performing? This should also run every release. Regression is where has any of the above here gotten worse compared to last release, right? So this is what the evaluation strategy would look like for this. In fact, evaluation is a very, very, very important component of any agentic system. You may be able to build agents, may be able to build multi-agentic systems, but if you're not able to evaluate them properly, you will never be able to take them to production, right? So that's the thing about evaluations. Observability, we already know about this from our traditional software development. Your evals tell you whether your system is good enough to ship, and telemetry tells you what's actually happening after you have shipped, and you need both, right? You could have telemetry at different levels. You could have telemetry every turn, right? So every time the user sends a message and the model responds, it gets logged with a unique trace ID, right? The token counts for input, output, everything, right? Which tools were called, how long each tool called take, and which model handled the call. All of that matters, right? Because when a user, let's say, reports that agent gave me a terrible answer on this one question, you can pull that exact trace ID and see everything. Then you have your per session telemetry. So this is the full timeline, the entire conversation log, every permission event, what was asked, what was approved, what was denied, right? And every sandbox event, what the kernel blocked, what was allowed, what was not allowed, right? So this is your per session telemetry. And then the aggregated is the dashboard, which is across all the users, all the sessions, where you track patterns, like where you find issues, whether when your compaction is firing, when are the retry rates going up, right? What percentage of permission prompts are getting denied and stuff like that. So that's about observability. Okay, so production reality. Yeah, this is something that we often go through in while we are building systems once we are in production. So this is the section that we have saved for the last, because so that you have enough context to actually understand what went wrong and why. Every architecture decision we covered exists because something broke first, right? And here you see these three real incidents, each one directly tied to a design decision we have already made. So in this April 2026 quality regression, this is the one that happened where three completely unrelated changes were shipped within weeks of each other, and it caused a drop in the model accuracy, not the model accuracy, the agent accuracy, right? Uh, each change was tested individually. Each of the change passed its own evals. But when all the three hit production at the same time, they compounded, right? The model was thinking less hard. It was working with stale context. So there were these different changes. If you want to read more about it, you can actually go to Anthropic's blog and read about this quality regression that happened, right? So now how they fixed this was that they made a stricter compatibility metrics, meaning you cannot ship changes to the model, the prompt, and the caching layer in the same release window. So because they did this thing where they made some changes to the model, some changes to the prompt and the caching layer, that's why everything compounded. So each one has to ship separately, so you can isolate which change caused which effect, right? And obviously a faster rollback path. Then there was another incident where the compaction system, the one which summarizes the old conversation to free up text, that would occasionally fail. Maybe the API timed out, maybe the summary came back malformed, and they did not have a circuit breaker. So before the circuit breaker existed, the system would just retry and retry and retry and retry indefinitely. Each retry was a full API call to the model, which means each retry would cost real money. And because compaction runs automatically in the background, the user had no idea that it was happening, and they just saw a API bill, a spike in their API bill, right? So the fix was a circuit breaker where you say that maximum of 3 retries and you're done. But this happened with Anthropic, right? It's so surprising to think about it. And then throughout 2025, there was a MCP bloat. So this is one we already spoke about in MCP, where you already know, right? MCP lets you connect external tools like GitHub or database or Slack, whatnot. So every MCP tool needs its full schema loaded into the context window, so the model knows how to call it. So early on, every tool schema was loaded upfront, right? At the moment the session started. So for users with just few MCP servers, this was fine. But the power users, they started connecting like 20, 30 servers, and suddenly 134K tokens of tool definitions were eating up the context window, right? So the fix, you already know, the fix was simple: do deferred loading, where load only tool names at startup, just short labels, and load the full schema only when the model actually needs to call the tool, right? So the pattern across all these three incidents that you see here, none of these were predicted, right? Nobody sat in a design meeting and said, what if 3 unrelated changes compound? Or what if compaction retries forever? Or what if users connect 30 MCP servers? All of them were discovered in production, right? By real users with real consequences. And each one produced a design decision, which is now permanent in Claude Code. That's the honest truth about production systems, right? The architecture diagram is clean, but it had some scars, right? All right, so these are the honest weaknesses which we have already spoke about before. We do not want to let the MCP be loaded eagerly, right? Sub agents are capped at one level. Eval coverage gaps are not enough, right? Eval suite is comprehensive, but some regressions can slip through them, right? So we have this new learning. Then compaction had no circuit breaker; it was retrying indefinitely. Model prompt binary coupling. So the three things can, if you make multiple changes together, they can compound, right? So this is what that is about. And sandbox bypass retraining, right? So the model, since it has learned from training data that It can retry failed commands with flags like dangerously skip permissions. It's not malicious. It has just learned that that flag makes the command succeed. So the kernel sandbox becomes the real safety code, but the model tries to keep going around it. And this tension seems to be still unresolved. Now, why we are sharing these honest weaknesses openly? Because I believe credibility only comes from honesty. So a system that really claims it has no weaknesses has never gone to production. That's the reason it's saying that. All right, so time to close the session now. This has been going for really long, but I'm really glad you all stayed here and listened to me patiently. Now, this is the final slide here. You remember the 5-layer architecture, the 22 design decisions. Now, this is your homework here. And I mean this seriously. Go back through these 22 design decisions on your own. Reread the slides where we introduce each one of them and ask yourself, does this decision still seem right? Would you have made the same choice? And where would you disagree with it, right? So the best way to learn a design is to really argue with it, right? So try to map all these design decisions at these different layers and see if they still hold. All right. So 6 transferable principles, right? We covered 22 decisions specific to Claude Code, but 6 of those design decisions are bigger than Claude Code. They would apply to any agentic system that you're building, right? And these are the patterns that get transferred from this session. So the model is the runtime. The model is the runtime. The model is the brain, but harness is something that makes it reliable. Model is non-deterministic, but the harness around should be deterministic so that you can really make a reliable thing which will deliver some value. It should be one main thread. Everything funnels through it, sub-agents, hooks, MCP tool calls, and all of that. Tools are contracts, not functions. Context is a memory bus, right? You design eviction and dehydration together. You can't just throw away old conversation to free up space. You have to put back things the model needs. Then defense in depth is a cost gradient, which means that cheap checks should fire first and expensive checks should fire later, right? And lazy load capability that we already spoke about on the MCP side. So these are the questions that you need to ask yourself when you design your own agent. If you're an engineer, ask these questions. If you're EM, ask these questions, TPM and PM. This is something that I would say I would ask you to think about, introspect after the session. And I hope the session has changed your mind in some good ways so that you would really want to ask these questions to yourself and find answers to them. And thank you. Finally, we are at the end of the session. We learned how to design Claude Code or a system like that. And I'm really grateful I was able to finish the session and you all stayed. So thanks, everybody. Let's hoping to see you in another class.
Yes, thanks, Yuvendra. I think it has been a wonderful session. Yes, I think we used a little more time than we intended to, but I think everyone stayed. I can still see so many of them still part of this. Yes, people are asking for the recording, so I've posted the YouTube channel link of IK, and you can go to the live section in that and access this particular recording later, because as Jivendra has given you guys homework, it'll be better that if you guys go through the session one more time if you want. So yes, thanks a lot everyone for joining in. I know it's late, just 10 minutes to 10, but yes, Jivendra, some compliments for you in the chat, so please go through that. And we have tried to answer some of the questions during the session, and I think most of it Jivendra covered anyway. But if you still have any questions about the program or a roadmap for you, specially built for you, customized for you, just get in touch with us. I've posted the calendar link of our program expert in the chat. So yes, that's our time, guys. Thanks a lot for joining in, and good night, and see you in the next session. Bye.
Yeah, sure. Thanks, everybody. Take care. Bye-bye.